Alright, so welcome to iChem lesson 14. Please make sure you have your viewing guide out in front of you. You're probably going to want a calculator so you can make sure that you're calculating along with me and you're going to get the same numbers. So we're switching gears a little bit to start talking about this idea of heat, but fear not, it ties right back into stoichiometry, and we're going to be practicing a lot of the same things you already know how to do. So first of all, energy is not matter. It's something different. Energy flows. The flow of energy into and out of the system can be involved with both chemical and physical changes. At first, we're really just going to go and look at chemical changes because that's what really applies to reactions and stoichiometry. But we'll move into physical changes as the unit goes on. So measuring the amount of energy flowing into and out of the systems is useful. Make sure you get this down. The units, the two main units of energy are joules and calories. Joules and calories. Sometimes we have kilojoules and kilocalories, but we know how to convert between those using basic metric unit conversions. Okay. So there's two classifications of reactions. One is endothermic reaction and one is exothermic reaction. In endothermic reactions first, the heat goes into the reaction, similar to the reactants. So you can consider heat as a reactant if you would like to in these kinds of reactions. In an endothermic reaction, the heat goes in. It has to come from somewhere, so the surroundings become cold. So for the next couple of days we're going to do some experiments with this, and you'll be able to feel that an endothermic reaction is occurring because it's pulling the heat from the surroundings, and you'll feel the cold actually on the outside of the beaker or the test tube or flask or whatever. The reaction curve part will be on the next slide. So jump down to flow of reaction for exothermic reactions. We'll come back to the reaction curve part, filling in the notes in a moment. Okay, so heat comes out of the reaction. Exo, think exit, heat is exiting. Similar to the products. The products are produced, heat is produced. When heat is produced, the surroundings come hot. So if you feel the outside of a test tube, and we could notice this maybe with some of the reactions we've already done in class, it will feel hot to you. Okay, so this is just on the outside scale, what's really going on. Let's look at what's called the reaction curve. So for an endothermic reaction, I'd like you to sketch this curve. The reactants are here at A. Heat goes into the reaction up really high, which is called the activation energy, and then comes back down low. Okay, this is the potential energy of the products here, where this is the potential energy of the reactants. Notice that the potential energy of the products is higher, so heat is required to form those things because they hold more energy themselves. So the true value of the delta H is going to be a positive number. In that case, it's the energy of the the products, minus the energy of the reactants. Now if we jump down or over to exothermic reaction, we already know that heat comes out of the reaction. If we sketch the curve, we would have our reactants. Every reaction has an activation energy, a hump that needs to overcome, but eventually the energy drops down to the products. The products have less energy than the reactants. So energy is released. Every exothermic energy value is negative. Get that? If you need to pause, come back and sketch them, do that now. We're going to move on to doing 2 examples. Alright, so here's our first example of how we would solve problems in thermochemistry. So in reality, we just are adding another conversion factor to our toolkit when we're talking about stoichiometry. So first, let's look at this problem. It says, how much heat will be released when 6.44 grams of sulfur reacts with excess oxygen? So we have one given. Now, instead of looking for mass of something else or moles of something else, we're looking for heat. Okay, so most of the time you'll be given an equation that looks like this first one. You have, this is familiar, 2 moles of sulfur react with 3 moles of oxygen to produce 2 moles of sulfur trioxide. Okay, the additional information now here we have is our heat of reaction. Notice heat of reaction is a negative number in this case. That negative means that heat is coming out of the system. This is released. This negative number just telling you that it's exothermic. Okay. Now that we know it's exothermic, we can kind of relate it to the reaction coordinate drawing that we talked about. The energy of the reactant is higher than the energy of the products, so energy is released. The surroundings would become hot. Again, an exothermic reaction. This is typically how you'll see the reaction written. This is a synonymous equation. Instead of writing it as the delta H on the side here, now I'm saying, because I know that heat is produced, I can say that heat is a product. So that for every 2 moles of sulfur reacted, 791.4 kilojoules of energy are released. It's just part of the equation. So now I can make a ratio from it. So first, I'm going to start with my given, 6.44 grams of sulfur. Okay. Before I can use my balanced equation, instead of grams of sulfur, I'm going to need moles of sulfur. Okay. Now this grams per mole is just molar mass. I grab my periodic table. I find sulfur. This is really glary. I find sulfur. It's 32.06. 32, we'll call it grams per mole. Now I have moles of sulfur, but I'm not looking for moles of any of my other products. I'm looking for energy. So I'm actually looking for kilojoules, okay? Heat. Let's look back at the balanced equation. This is a new ratio that comes from my balanced equation. Moles of sulfur, same old from the ratios in balanced equation, 2. But now I have energy. I'm taking that number, it's a product, 791.4 kilojoules. Okay. This is a new mole to energy ratio coming from your balanced equation, where your heat is produced in the reaction. So I come over here, I take my calculator, and I plug it all in. And I get 6.44 divided by 32 times 791.4 divided by 2. And I end up with 79.6 kilojoules released. Okay. So this is an example of an exothermic reaction when heat is released. Let's do one more example. Okay. Now, in this case, the equation given to me is H2O, water, plus carbon, plus 131.4 kilojoules yields 1 mole of carbon monoxide and 1 mole of hydrogen gas. Now, this isn't typically how you will see it, but this is analogous or synonymous to this equation here, where you would be given the delta H of the reaction. And in this case, there's no negative there. So that means that this amount of energy is added to the system for this reaction to proceed. Okay, so it's added. Means it's one of my, I count it sort of as a reactant. So that means energy is added to the system. The energy of the reactants is lower than the energy of the products. Okay. In that case, heat will be added. It has to come from somewhere. It takes the heat from the surroundings. The surroundings become cold. This is an endothermic reaction. Okay. Calculations are really done the same way though. You have 1 metric ton, in other words 1,000 kilograms of coal. Okay. I want to know how much energy is needed. First, from kilograms, to be able to use my equation, I need to get moles. This is one weird added step we're not used to doing. I'm not used to having kilograms. I'm used to having grams. There's 1,000 kilograms in 1 gram. So now I have grams of carbon on top. I want grams of carbon on the bottom. I want moles of carbon here. Grams per mole of carbon is my molar mass of carbon from the periodic table. It's 12. Now I have moles of carbon. I'm ready to do my mole to energy ratio, where I have moles of carbon and I want kilojoules. The ratio comes from my balanced equation. You have 1 carbon, and for every 1 carbon, you need 131.4 kilojoules. So I plug it into my calculator. 1,000 divided by 1,000 divided by 12 times 131.4. So 10.95 kilojoules of energy are needed for this reaction to occur. Okay, notice I'm not just putting a number with units. For this endothermic reaction, energy is needed. For this exothermic reaction, energy was released. Those are important distinctions. Come prepared to class tomorrow to perform one of these or many of these calculations on your own. So review if necessary.